Imagine a universe reflected in a flawless mirror. Electric charges would flip, but forces should behave identically. A left-handed neutrino becomes right-handed. Clockwise decay unwinds counterclockwise. Physicists give names to these reflections. C changes particles to antiparticles. P reverses left and right. Test them together. CP symmetry and reason suggests nature ought to stay impartial. But peer into the subatomic theater of the weak interaction, and the mirror cracks. Beta decay, for example, throws electrons preferentially in the opposite direction to a nucleus's spin. Always to the left of motion, never to the right. This handedness is baked into the mathematics. Only left-handed neutrinos and right-handed antineutrinos participate. Swap charge and parity, and the weak force does not recognize its own reflection. The betrayal is tiny in everyday life, yet profound in implication. If mirrors can lie at the quantum scale, then matter and antimatter need not balance exactly. This bias, subtle as a misplaced footnote, creates a loophole in conservation stories told since Noether. Matter can emerge with a hair's advantage, provided the rules bend just enough at pivotal moments. Identifying where and how those bends occur is more than academic. It answers why the night sky shines with galaxies instead of a uniform haze of annihilation light. Enter the humble Kaon, a meson built from a strange quark and a down antiquark. In 1964, at Brookhaven National Laboratory, James Cronin and Val Fitch fired neutral kaons through a beamline designed to isolate those that normally lived longer. Particles expected to decay only into 3 pions, a C-pure specting mode. To their astonishment, some of these long-lived kaons decayed into 2 pions, a channel forbidden if CP symmetry were absolute. The result was minute. Roughly 1 in 500 decays broke the mirror, but minute was enough. That sliver of excess could, in the furnace of the early universe, snowball into the 1 in billion matter surplus that outlived mutual annihilation. Cronin and Fitch's bubble chamber photographs. Delicate curls frozen in liquid hydrogen were the first direct evidence that CP symmetry could fail. Follow-up experiments deepened the rift. CERN's Na-48 and Fermilab's KTeV refined the asymmetry. Today, Japan's Bell 2 and CERN's LHCb extend the hunt to heavier B mesons, where the standard model predicts even larger CP cracks. Each dataset narrows possibilities for new physics. Unseen heavy quarks, exotic Higgs cousins, or lepton number tricks tied to neutrino masses. The Kaon's quiet treachery taught cosmology a vital lesson. Cosmic balance can pivot on an almost invisible preference. The quest now is to measure that preference everywhere it might hide, until the arithmetic of existence adds up without hand-waving, leaving us either satisfied or staring at a doorway to forces still unnamed. At CERN's LHCb and Japan's Bell to experiment, colliding protons and electrons birth torrents of B mesons containing bottom quarks. These mesons oscillate between matter and antimatter forms, much like kaons, but their heavier mass amplifies the weak force's complex phase, making CP-violating effects easier to spot. Physicists sift through quadrillions of decays, comparing how often a B meson becomes a kaon plus pions versus how often its antimatter twin does. Angular distributions, decay times, and charge imbalances all paint the same picture. The mirror still lies. And the lying follows patterns predicted, yet not fully exhausted by the standard model. Intriguing tensions appear in rare transitions. If confirmed, they may hint at undiscovered particles carrying their own symmetry quirks. Meanwhile, tabletop experiments chase CP cracks in different arenas. Ultra-cold neutron traps probe the neutron's electric dipole moment. Atomic clock comparisons test whether fundamental constants drift with Earth's motion through the cosmos. Each negative result narrows theory. Any positive signal could rewrite cosmology overnight. The quest is both forensic and prophetic. Measure the weakest biases in quark decays, and you may decode how 1 billion to 1 preference in the early universe blossomed into every galaxy shining tonight. Long before data arrived, Andrei Sakharov drafted a recipe for cosmic imbalance. First, baryon number must be violated. Processes must occasionally turn quarks into leptons or radiation. Second, C and CP symmetry must break, so matter-favoring reactions marginally outpace their antimatter twins. Third, these reactions must occur out of thermal equilibrium. Otherwise, forward and reverse processes cancel the gains. Several theoretical kitchens try to cook the universe's surplus. Lectoweak baryogenesis uses high-temperature fluctuations of Higgs and gauge. Fields fullerene to violate baryon number, while CP-violating phases in the Higgs sector tip the odds. The scenario demands extra Higgs-like particles. The LHC has yet to taste them. Leptogenesis begins with heavy right-handed neutrinos decaying asymmetrically. Then lets fullerenes convert lepton excess into baryon excess. Upcoming neutrino mass measurements and neutrinoless double beta decay hunts may confirm or close that kitchen. Whatever the mechanism, the numbers are stark. For each billion annihilations, one lonely baryon slipped through, carrying with it all future stars, planets, and possibilities. The tiniest fissure in CP symmetry thus acts like a cosmic seed crystal. It's imperceptible in isolation, but decisive when multiplied by the furnace of the Big Bang. In the next part, we venture beyond kaons and mesons to explore hidden symmetries that might still wait in the shadows. Promising answers are deeper mysteries about why reality chose something over nothing. Picture the newborn cosmos as a vast ballroom where matter and antimatter waltz in perfect pairs. Each step is mirrored, every twirl matched by its inverse until, somewhere in the choreography, the mirror cracks. Out of a billion couples, a single proton misses its antiparticle partner. That survivor, and others like it, seed every star now lighting the sky. The margin is ludicrously thin, a baryon-photon ratio. Yet the cosmic microwave background, glowing at 2.7 Kelvin, confirms it. Those relic photons outnumber protons by the same factor everywhere astronomers point their antennas. The surplus traces back to CP-violating decays in the universe's first instance. Perhaps heavy right-handed neutrinos that split into leptons ever so slightly more often than antileptons. Electroweak's fullerenes then rewrote that lepton bias into a baryon surplus, locking protons and neutrons into the future. Today, each sunset, every breath, and the iron in a compass needle testify to that billion-to-one asymmetry. Physics did not simply prefer matter, it preferred it by the narrowest conceivable vote. Leaving behind a cosmos rich in structure, yet sparse enough that light could travel, cool, and eventually give rise to questions like these. We have measured the fracture. CP violation is real, but the standard model's tiny bias cannot account for the vast architecture of galaxies. Somewhere beyond present energy frontiers lurk deeper breaks or altogether new symmetries that magnified the imbalance. Did supersymmetric particles tip the scales, only to hide beyond the reach of current colliders? Do neutrinos violate lepton number and whispered? Neutrinos decays deep underground? Could dark sector forces echo a symmetry we have yet to name, shaping invisible matter into halos that cradle every visible star? In the final segment, we will step back from molecules and galaxies to reflect on what this tapestry means. Why does a universe stitched from probabilities and partial patterns feel, at human scale, so solid and comprehensible? How do broken symmetries grant not only structure, but memory, music, and meaning? Join me for the outro, Harmony in the Imperfect, where we'll gather every thread. Noether's ledger, the sun's quantum heartbeat, the cracked mirrors of CP violation, and the snowflake melting in your palm to one final reflection on a cosmos forever poised between balance and becoming. Step back with me, far enough that continents blur into mottled greens and oceans into a single shimmering band. From this vantage, the entire planet is a snowflake of geology. Mountain ridges radiating like crystal arms, river deltas branching in mirrored pairs, hurricane spirals twinning in opposite hemispheres. Even here, symmetry whispers. Yet peer closer, and each valley deviates. Each cloud tilts a fraction off its counterpart. Those slivers of asymmetry keep rivers flowing, winds circling, life forever improvising new forms. Across our journey, we trace that balance from the mathematical to the tangible. Noether showed us that whenever the universe refuses to change under a certain motion, be it a slide through space or a tick of the clock, something precious must be conserved. That hidden bookkeeping steadies Earth in orbit, lets diamonds endure, and times every photon forged in the sun's core. Then we slipped inside that stellar furnace to watch quantum tunneling soften an otherwise impassable electrostatic wall. Proving that perfect rules can harbor humble loopholes, we saw the weak force crooked in its mirror. Turn protons into neutrons just rarely enough to stretch a star's lifetime across billions of dawns. We rolled time backward to a hot, symmetric embryo of a universe so uniform it almost erased itself only to witness symmetry snap in stages. Each fracture unlocking new layers of complexity. Mass from the Higgs field, matter's narrow victory over antimatter, density ripples that would one day blossom into galaxies. Closer to home, we wandered through snowfields, silicon wafers, and single sheets of graphene, noting how translational order and rotational elegance guide electrons, bend light, and carve ice. Along the way, symmetry's missteps proved as vital as its rules. Broken mirror laws color butterfly wings, twisted graphene angles birth superconductivity, and a chiral bias in amino acids lets proteins fold with purpose. Beauty, it seems, is born where order meets deviation, where the universe keeps its promises, yet allows a margin for creativity. Perhaps that is why humans find symmetry comforting but perfection dull. Our brains are wired to recognize pattern, yet our hearts quicken at the unexpected flourish. A syncopated rhythm, a tilted facade, a comet that refuses a circular path. We are children of fractures. Every atom in our bodies survived a 1,000,000,000-to-1 matter bias. Every breath depends on weak force irreverence. Every thought rests on electrochemical pulses choreographed by quantum statistics. So the next time frost paints your window, remember the celestial genealogy of those delicate hexagons. Recall that a hydrogen bond's 120-degree embrace echoes. It's the same geometry that lets carbon weave graphene and Saturn sport its icy rings. And know that without the tiniest departures from symmetry, without the gift of imperfection, there would be no rings. No ringside observers, no stories to tell. This is cosmic canvas, where the universe is not only studied, but painted in meaning. Until next time, keep asking, keep looking up, and never stop wondering.